Intro to Calc. Hope you guys are having a fantastic day. Today we are doing the last section of Chapter 2, and it's the topic of the day is differentiability. And that basically begs the question, what types of functions are we allowed to take derivatives of? And in what cases, like there are some functions that you can differentiate most places, and there are functions like where there are some spots where you have problems differentiating. And by differentiate, I mean take the derivative. It's just a fancy word for find the derivative of. Okay, so that's kind of what our topic is today. So we're just going to kind of like observe different types of functions and talk about when you're allowed to take the derivative and not. Just as a refresher, recall the definition of a limit existing. And a limit exists if the limit from the left and the limit from the right are also, I think the video like flips me backwards, so I'm not quite sure if I said the right side. But anyways, the limit from the left and the limit from the right are equal to each other. So you have the limit, so basically like you have the same, the function is approaching the same value from both the left and the right hand side. If on the other hand you have the function approaching two different values from the left and the right, then it's not, it doesn't exist. The limit does not exist. Okay, so again, a limit exists if the limit from the left is equal to the limit from the right, and that limit, that number that they both approach is like not infinity, because then it also doesn't exist. This term differentiable, that just means that a function is differentiable at a point if you can take the derivative at that point. Okay, so a function f is differentiable at x or at a point if the formal definition of a derivative, right, which is the limit of the difference quotient, if that limit actually exists, namely it doesn't blow up to infinity or it doesn't like go different points, that's what it means to be differentiable. Okay, so what this actually looks like, there's like three general indications that something is not going to be differentiable. The first is if the slope at the point is a vertical line, because the slope of a vertical line is 1 divided by 0, which is infinity. So that would be one indication that it is not differentiable at that point. Two is that the graph is not continuous at that point. So if you have any sort of discontinuity whatsoever, it can't be the function can't be differentiable. Basically, because if the function doesn't exist there, then you can't take like the derivative. You can't take the slope of the tangent line. You can't find the slope of the tangent line. And then the last indication that something is not differentiable is if you see sharp corners. So in order for something to be differentiable, it has to be continuous and it has to be smooth, like nice and like flowy kind of. Because the sharp corners, and I'll show you why, but sharp corners on graphs are not differentiable. So if you look at some of the examples that I gave you, here's f and g at the top. So f of x is continuous, right? I can draw the whole thing without picking up my pencil. And there are no spots where the derivative would be undefined or like a straight vertical line. Now this is pretty steep, but it is not like an asymptote. It's not like a vertical, completely vertical line. And I don't have any jumps or skips or anything. So f of x is continuous and it's also differentiable. G of x, on the other hand, is different because you see that sharp corner at 0, right? This is the absolute value function, but since there's a sharp corner at 0, it's not differentiable. And that's basically because the derivative coming in from the left is -1, right? The slope of this tangent line is -1, and the slope of this tangent line is +1. And so when they come in, they hit at a sharp corner, and there's no, like, they don't meet, their derivatives don't match up. Like, you don't have the same derivative coming from both sides. So again, so G prime is -1 here, G prime is +1 here, and since they don't, it's not a smooth transition between the two of them, where the derivative is approaching the same value, then the derivative does not exist there. So that is not differentiable. And at 0, right, like some people try to like make a horizontal line or something at 0, but that's not the slope of that point. The slope is, from the right, the slope is +1, and from the left, that slope is -1. So that's a problem, because they're not the same. So p of x is this function here, and you can kind of see, right, that it's not continuous at x equals 3. And also, as you go up higher and higher, getting closer to 3, that line's going to get to be a vertical slope. And so that derivative at that point is going to be undefined because it's approaching positive infinity here. And then on the right-hand side, that slope's approaching actually also positive infinity because the slope is increasing. But you can't have a slope of infinity. Like, that doesn't work. So the function is not differentiable at x equals 3. It is also not continuous at x equals 3. And last but not least, q of x, right? Q of x is continuous up until 3, and then it jumps down to 1 at 3 and keeps going. So problem number 1 is the function's not continuous. So at this point, so it can't be differentiable because the slope here is not going to be the same as the slope here, and because it's a discontinuous function there, you can't have a derivative. So this is just kind of another example of a discontinuity. So it's not continuous, but it's also not differentiable. And then the last thing is that there's a Theorem 2.1, and it's pretty self-explanatory, but a differentiable function. So if you have a function that's differentiable everywhere, it has to be continuous. So again, if you know a function is differentiable, it has to be continuous. But not every continuous graph is differentiable. Case in point, g of x, right? This is continuous but not differentiable. But if you know it's differentiable, you know that it has to be continuous. And that's pretty much it. Short lesson today. Hope that helped. Hope it makes sense. And I will see you in class. Bye!